Is part two of primary secondary versus variable primary flow and describes the ideal operation of variable primary flow, including its advantages and disadvantages. Here is at the top our typical primary secondary system that you were looking at before, and down at the bottom we have variable primary flow. And what you'll notice is the differences are that primary secondary is, again, typically on the primary side, going to be with dedicated pumps, and secondary unheadered. But now we take these two sets of pumps and combine them together into one set of pumps that are all headered together. Now this doesn't mean, again, just like primary secondary, you couldn't dedicate these pumps. But if you do dedicate these pumps, then you can hurt some of the possibilities that you can do for control that can optimize energy savings. You'll also notice that we have shown automatic isolation valves here. This is for a specific purpose. We didn't really show much up here on isolation valves, but this is for a specific purpose that we'll discuss later in part 5. You'll also notice that we still have some sort of what looks like a common pipe down here, but it's closed off with a bypass valve, a two-way valve that is closed normally when you're during normal operation. And it's controlled by a flow meter here, although it can also be controlled by pressure differential across the evaporator shells. It's just that flow meter is better, and we'll discuss that in part 5 as well. So that's the differences. This system is simpler. It has one set of pumps, and it's preferred that these are headed. Looking at this system, just like we did with primary secondary in the last section, is we have a design of 100% load here. That's our 6,000 tons, our 9,000 GPM. Unlike the primary secondary system that had 50 feet of head in the primary and 100 feet in the secondary, we have a total head here of 140 feet. And we'll explain that a bit later as to why that went down. So we have 9,000 GPM. Our bypass is closed. Our bypass is strictly there to maintain minimum flow through operating chillers, which is usually one when you get down to that point. And so it's all one loop. As long as this is closed, it's completely just one loop instead of two. At 75% load, we'll drop down to the same to 6750 GPM, just like we did before in the primary secondary. And this 6750 will pump through the whole system. Because these are 3,000 GPM pumps, I still have to run all three. I have to run all three chillers at a 16-degree delta T. At 15% or 50% load, I'm now down to 4,500 GPM, which is half of the 9,000. And 4,500 is traveling through the system. Again, our delta T is remaining constant. It's still 56 to 40. But I now can shut off a chiller and a pump if I choose to. I don't have to shut the pump off because by having it headered, I can choose to run 3 pumps at a slower speed than 2 pumps at a faster speed. That might turn out, if the efficiency of the pumps are good, might turn out to be a more efficient way to operate. This is the reason why having headered can be a superior in energy, not to mention reliability and so on. And I'm 25% load. I'll be down to 25% GPM or 2250 through the system. Again, 56 to 40 because delta T is remaining constant and it's flow that's varying with load. Now I can shut 2 chillers off. I can shut 2 pumps off, or I can shut 1 pump off, or I can leave all 3 running, whatever turns out to be more energy efficient depending upon the control algorithm that is used. The advantages of variable primary flow, VPF, is that it has a lower installed cost than primary secondary, usually in the neighborhood of about 5%. The reason for that is I have no secondary pumps, therefore I don't have the wiring of those pumps, the piping of those pumps, the rigging of those pumps, the installation of those pumps, the control of those pumps. All that goes away, and I only have one set of pumps that I have to do all that to. That generally speaking are the same pumps in BPF as the secondaries in primary secondary, just with a bigger impeller or a higher diameter impeller in it. This number is offset somewhat by the two-way valve, bypass valve and control that you have to add, and the potential for higher PSID rated valves that are two-way valves that are the load valves and the bypass valve, because they have to handle a higher head, a potential. and there's more complex controls. But overall, between the reduction in cost on secondary pumps not being there and the addition of these additional controls and so on, we still have a net advantage in install cost with VPF of about 5%. In addition, there's less plant space needed because I don't have to site the secondary pumps, which means I can now use that space as rentable space. And there's a better pump energy consumption. Now, most everyone knows that when you variable speed the entire plant, you're going to save energy, more energy than you would if you had part of the plant on constant speed versus variable speed. But there are two other components of the three that also come into play, and one of them is higher pump efficiency. What I mean by that is if I were to size a secondary pump for, let's say, 2,000 GPM, I just grabbed this set of pump curves, for a secondary pump for 2,000 GPM, and at 100 feet ahead that we had talked about, then I would be around 80% efficient on that pump. And this will depend, of course, on where I am in my selection. But when I go to 140 feet, that we remember was our variable primary flow, then I move up to here on a 12.5-inch impeller. And now I'm up to 86% efficiency. Now this can vary how much this is. It sometimes can even go down, but most of the time it goes up, depending upon where you're selected versus BEP. If you're to the left or to the right, can change that. There's also the issue with the pump efficiency that the primary pumps being at lower heads of, in this case, 50 feet, is going to have 1,200 RPM motors, and it's going to be lower down in the pump curves. And generally speaking, you're going to see a lower efficiency on those pumps. In this case, let's just assume that we'd be in the 70s. Let's pick 74%. But when you add the 74 against 50 foot ahead versus the 100 feet at for the secondaries, then you have an overall efficiency improvement by going to variable primary flow on the pumping system. There's also a lower pump design head. Now, you sort of alluded to this earlier, but remember our primary loop from our primary secondary system was 50 feet, and our secondary loop was 100 feet. But that 100 is got two components of it, and one of it is the head loss right around this secondary header. And that includes the strainers, the valves, the pumps, etc. There's a 10-foot head loss, or around 10. So then the system loss out here is only 90 feet. Well, I don't have this 10 anymore because I've eliminated those pumps down here. So now I have 50 plus 90 instead of 50 plus 100 for 140. So now my head is reduced at all operating points, not just at design, throughout the entire operation of those pumps. And remember that our pump energy is flow times head divided by 3960 divided by the pump efficiency. And our pump efficiency got better, and our head went down, as you can see here. Head went down 10 feet, and my pump efficiency went up. So overall, I'm going to see a lower design horsepower, lower design brake horsepower, and therefore lower energy at design and every operating point for that pump throughout its operation for years. To illustrate what that amounts to in this particular case, if I had 9,000 GPM in my primary times my 50 feet divided by with a 74% efficiency, I get the 153 horsepower. And my secondary pumps, 9,000 times 100 feet with my efficiency at 80% gives me 284 for a total of 437 horsepower at design for that primary secondary system. Whereas with VPF, I've got 9,000 times the 140 divided by my constant and my 86% efficiency, which gives me 370. And you can see the advantage here in horsepower is pretty significant. So it's not just that you're at variable speed, which is my last one. It's not just that you're at variable speed, but it's also your pump efficiency is better, the design head is usually lower, and now, of course, my entire system head is variable sped. And another added attraction to variable primary flow is that although it's susceptible to low delta T problems, just like primary secondary, there's less impact, less negative impact on due to low delta T. Disadvantages of variable primary flow is that you could have a higher PSID rated two-way valves in the system. That's the load valves, the bypass valve. They could be higher, but 95% of the time they won't be. It'll be the same. It does require a more robust or complex calibrated control system. This is because we now have the bypass valve in there. If we're going to take advantage of the headered pumping in the VPF system, then it's going to have some more requirements, because clearly if you're running 2 chillers with 3 pumps, that's going to be different than just cycling the pumps off with the chillers. Now, another disadvantage is that it requires a coordinated control of the chillers, isolation valves, pumps, which means that there needs to be a meeting during the design phase before everything is installed and everything, with the consulting engineer, with the chiller folk, the chiller supplier, or at least the specified one, the pump supplier, the control supplier, and the valve supplier, to make sure everyone understands the sequence of operation that the consultant wants to use, and make sure everyone's limits are out there so that there isn't any problems with the system later. If that is done, that meeting ahead of time, then the potentially longer commissioning time goes away. Really, there's no difference in commissioning if you do that ahead of time. If you don't do it ahead of time, then of course the extra time during commissioning is doing it then. So you can have the meeting before, you can have it after. It's just better to do it before because it's less costly. The last item is probably the most important reason to maybe avoid VPF, and that is, what is the sophistication of the operators, of the user, of the owner that's going to be using this system? If they don't have training and retraining programs, if they don't have people that understand VPF, that won't look at 3 pumps running versus 2 chillers and think something's wrong and shut the system off, there really needs to be greater operator sophistication levels on training and understanding of VPF if you're going to put it on a system. This is the end of chill water piping types, part 2.